In this lecture, we're going to do a quick refresher on exponents and radicals. Everything in this video is from prerequisite courses. I know you've been exposed to all of this before. We're just going to do a quick recap of some definitions and do some examples, so all of these rules are on the tip of your brain rather than buried somewhere where you have to dig them up. Let's start with the notation that we use for exponents. If n is a positive integer and we write it as a superscript on some base a, that means n factors of a multiplied together. So the generic way to read this is to say a to the nth power. Or sometimes we just say a to the n. When n is 2, we'll often say a squared. When n is 3, we say a cubed. Otherwise, we use this ordinal. So when n is 4, we would say a to the 4th power, and so on. Let's do some numerical examples. The first example here has a notational issue. This says -5 squared. We're squaring the base -5. And I know the square is on -5 and not just the 5 because of the grouping symbols, the parentheses. The superscript 2 there is on the grouping symbol, and so we're repeating everything inside the grouping symbol. We need 2 copies of the expression inside the parentheses. And now we do the multiplication. I didn't write a multiplication symbol there because it's implied. -5 times -5 is positive 25. The next 2 examples are more straightforward. 7 cubed is how we would read this one. It means 7 times 7 times 7, which is 343. 2 to the 9th is how we would say this. When the superscript is something that other than 2 or 3, we read it as an ordinal, so 2 to the 9th. And this is 9 copies of 2 multiplied together. And 2 to the 9th is 512. You can see one of the uses of exponents is just to be concise. 2 to the 9th is much more compact than writing out 9 copies of 2. The last example again tests our understanding of the order of operations and notation. In the first example, the exponent is on -5 because the exponent applies to everything inside the grouping symbol. In this last example, there is no grouping symbol, and so the exponent is on the thing that directly precedes it, which is just the 3. So while I'm going to repeat 4 copies of 3, I do not repeat the negative. The negation stays out front. 3 to the 4th is 81, and then I negate that and I get -81. The exponent applies to the symbol that immediately precedes it. If that symbol is a grouping symbol, then we repeat everything inside the grouping symbol. You can see that I wrote it by repeating the entire grouping symbol, just to make it a little more clear. In the last example, the symbol that immediately precedes the exponent is just the base 3, and so that's the only thing that gets repeated, and then we do the arithmetic. 2 more rules. If a is a non-zero base, then a to the 0 power is equal to 1, and a to the -n power is just the reciprocal of a to the n power. Here's some examples to solidify those rules. Our first example has a ridiculous expression inside the parentheses, 37 times the square root of 2 plus 5 pi, but that entire expression is raised to the 0 power. That exponent does not distribute individually to each term, it's on the entire expression. And we said on the previous line that any non-zero base to the 0 power is equal to 1. Well, 37 times the square root of 2 plus 5 pi definitely isn't 0 because that's the sum of 2 positive numbers. And so this is equal to 1. It wouldn't matter what this base is as long as it's not 0. 0 to the 0 power is undefined, but any non-zero base to the 0 power is equal to 1. Now the negative exponents. The rule says that you can rewrite a negative exponent by taking the reciprocal of the base and raising it to the positive power. Another way to say that is you take the reciprocal of the base and raise it to the nth power. So we can apply that to the last 2 examples. For 6 to the -3, I would write it just like the rule says. I would put the 6 down in the denominator and make the exponent positive. And 6 cubed is 216, so this is 1 over 216. For the last example, I wouldn't rewrite it using that same rule. Instead, I think about what it means. I take the reciprocal of the base and I raise it to the positive power. So rather than rewriting it as 1 over 2/9 squared, which is correct, I would just write this as 2/9 squared. I take the reciprocal of the base and I raise it to the positive power. You might say, well, why don't we do that here? Well, it's because 1 to any power is 1. So writing that as 1/6 cubed, while technically correct, is unnecessary because when you take 1 times 1 times 1 in the numerator, you're just going to get 1. So we just applied the exponent to the denominator. When you've got a fractional base, though, it's more convenient to just take the reciprocal of the base and then change the power to a positive number. 2/9 squared means 2/9 times 2/9. When you multiply fractions, you multiply the numerators and you multiply the denominators, and so this is 4/80. But in algebra, we often use exponents for conciseness with variable bases. And rather than trying to simplify down to a single number, we might just be trying to simplify an expression as far as we can, using some laws or some rules of exponents. Here's a list of some common rules of exponents. The rule in the upper left here says that if you multiply two exponential expressions with the same base, you can consolidate that into a single exponential expression by adding the exponents, retaining the base. You don't change the base, you just add the exponents. The second rule shows what you do when you raise an exponential expression to a power, what I call the power to a power rule. When you raise a power to a power, you multiply the exponents, again retaining the base. The base stays the same. The rule at the bottom of the left side is a product to a power. When you raise a product to a power, you raise each factor to that power. So a times b, all raised to the m power, is a to the m times b to the m. Now, people who are coming into college algebra after a break, remember this rule and sometimes extend it to a rule that does not exist. It is not true that if you raise a sum to a power, that you can raise each term to that power. That is not true. It works in special situations, like if a was equal to 0 or if b was equal to 0, but in general, that rule does not work. It does extend to division, though. If you take the quotient of two expressions and raise that to the mth power, that's like raising the divisor and the dividend to the mth power. I think of this as a fraction to a power. Another way to say this is, when you raise a fraction to a power, you raise the numerator and denominator to that power. In the last example on the previous slide, I used the definition of an exponent, but we could have just squared the 2 and squared the 9 to get the same result. The last rule here is called the quotient rule, and it basically says that if you divide two exponential expressions with the same base, you can consolidate into a single exponential expression by subtracting the exponents. A is not allowed to be 0 here because division by 0 is undefined. Let's do a couple of examples that demonstrate most of these. We're going to save one for later. The first example is the product of two expressions, negative 3x to the negative 2 times 4x to the 4th. So we know that multiplication is commutative and associative, so we can multiply these parts together however we like. We can take the negative 3 times the 4, that's negative 12, and then we take x to the negative 2 times x to the 4th, and that's where this first rule comes in. If you multiply two exponential expressions with the same base, you can add the exponents. Negative 2 plus 4 is positive 2, and so we get an answer of negative 12x squared. Again, that square comes from multiplying those two exponential expressions together and adding the exponents. At this level, I don't expect my students to show this kind of work. You don't have to show me where the 2 came from. The last example on this slide says the cube of 2x squared times y squared, all divided by 4x to the 4th y squared. There are a few different ways you could start this problem, but I'm going to follow the order of operations, and the order of operations would tell me to handle this cube first. So I've got a product raised to a power. That's this third rule right here. So I cube the 2, and I cube the x squared. I'm not doing anything with any of the other factors, so I'm just going to copy them down. Again, the order of operations says I'm going to handle these exponential expressions. You might be chomping at the bit to cancel the y squareds. That's perfectly acceptable here, but I'm not going to do it that way. I'm going to follow the order of operations, but you'd be right to do that. 2 cubed means 2 times 2 times 2, that's 8. X squared cubed is the power to a power rule. When you raise a power to a power, you multiply the exponents. So we get x to the 6th. And now you have to remember the roles of the numbers here because you're going to do different operations. This is 8 divided by 4. These are constants, what we call coefficients. And here we're dividing 8 by 4 and we get 2. When we divide x to the 6th by x to the 4th, that's that quotient rule. And so we're going to subtract the exponents. And it's always the exponent on top minus the exponent on the bottom. 6 minus 4 is 2, so that's x squared. y squared divided by y squared is 1, and you can think of that in two different ways. The obvious way is that if you divide a non-zero number by itself, you get 1, but we could also use our new quotient rule. Just to demonstrate that, if I take y squared divided by y squared on its own, the quotient rule says that I subtract the exponents, and 2 minus 2 is 0. And what did we say y to the 0 is? Well, it's 1. And when you divide two expressions and you get 1, we say that they cancel. A lot of people will actually cross them out when they do that. It's kind of a visual way of showing yourself that you've canceled those away. There are no copies of y left in our final answer. This reduces down to 2x squared. You may have noticed there's one rule we haven't used yet, this one in the upper right-hand corner, but there's an example coming with that. The other four we've practiced. Before we get to that example, though, we're going to need to take a detour through radicals, so here's a quick reminder. We call this notation here a radical, and the number in the little nook here is called the index of the radical. I'll usually just call it the number in the nook, but the technical name is the index. And you read that as saying nth root, and if there's no index written, it's an implied 2. We call that a square root. What do these radicals mean? Well, it depends on what you have underneath the radical, what we call the radicand. If the number under the radical is 0, then the nth root is just 0. The nth root of 0 is 0. If the number under the radical is positive, then the nth root of a is the unique real number b, such that b to the n is equal to a and b is positive. Now when you read that rule, that sounds confusing. So before we get to the last two rules, let me jump to an example. The first example here is a radical with a 25 underneath it. And anytime that you have a radical with a blank index, it's an implied 2. So this is a square root. We don't usually write it, and it bothers me to look at it, so I'm going to erase it. But there's an implied 2 sitting there. So the answer to this, according to the rule, is some number that we can square in order to get 25. We have to fill in that blank. And here's the issue. There are actually two numbers that would work there. Both 5 squared, and as we saw earlier, negative 5 squared would give you 25, right? That was our first exponential example. Negative 5 squared is 25, positive 5 squared is 25. So how do we know which one to choose? Well, that's where this notation's technicalities come in. We call this a principal nth root, and so we choose a specific one. Which one do we choose? Well, this says that for a positive radicand, we choose the base that's positive. So while we have two choices, the one that we're going to select as our principal square root is the positive one. Since 5 squared is equal to 25 and 5 is the positive choice, that will be our principal root. Let's look at the second example from the same context. This says the principal cube root of 8. Going back to the rules, if the number underneath the radical is positive, then we just have to find the real number that we can raise to the power of the index in order to get the number under the radical. So in other words, we're trying to fill in this blank with a positive number. So what number do we have to raise to the third power in order to get 8? Well, we just saw that in a previous example as well. We saw in this example that 2 cubed is equal to 8, and 2 is a positive number, so it's the one that works. We know that the principal cube root of 8 is 2, since 2 cubed is 8, and 2 is the positive choice. It turns out that 8 has two other cube roots, but they fall into this other set of numbers that we call non-real numbers. We're going to look at one way to find the other cube roots of 8 in a future lecture. The last example gives us a negative number under the radical, and here we have to be careful. If the number under the radical is negative and the index is odd, then we follow the same idea as before, except we choose a negative number as our principal root. It turns out that a positive number won't work here, so we choose a negative number. So we're trying to answer the same kind of question. We're going to raise some base to the same power as the index and hope to get the radicand. But we know that the number that goes in the blank has to be a negative number. A positive number won't work because if you raise a positive number to the fifth power, you get a positive result. So the answer has to be negative. A little bit of thinking, and you'll realize that -1 works here. 5 copies of -1 multiplied together would come out to -1 because the sign just alternates as you go. And that's a negative choice. -1 is less than 0. So this answer is -1. You don't see an example of this type here because we're going to deal with it later, but let me just bring this up now. If you've got a negative radicand and the index is even, then the nth root of a is not a real number. It doesn't belong to the set that we call real numbers, and I hate that name. I hate that the name real numbers caught on. All numbers are abstractions. They're not real in the sense that you can touch them or anything like that. And some really smart person, you've probably heard of him, Descartes, as in I think, therefore I am, he referred to real numbers and imaginary numbers, and somehow that's been twisted to mean important numbers and numbers that you'll never need. And while it's true that you don't need imaginary numbers to balance your checkbook, it turns out that imaginary numbers had all kinds of important uses later on, like in electronics and so on. Like the math that's used so that your precious little cell phone will get its signal, that's based on imaginary numbers. They have a stupid name, but they're not useless. It'd be like if your parents were weird and they named your sister Imaginary. That wouldn't make her imaginary. She just has a stupid name. It's the same with the numbers. Real numbers, imaginary numbers, you got to get past that and just realize that those are labels. Sorry about that little rant there, but it's always bothered me that these are called real numbers. Real numbers. Stupid name. Anyway, those non-real numbers will come up in a future lecture. We'll talk about those there. 2 more bits of notation here. This is the link between exponential notation and radical notation. We can represent the principal nth root of a using an exponential notation. We use the exponent 1 over n. So a to the 1 over n is equivalent to the principal nth root of a. So for example, a to the 1/2 means the principal square root of a. And the principal cube root of a can be rewritten as a to the 1/3, and so on. If you have a fractional exponent whose numerator is something other than 1, then you just raise the radical to that exponent. We can actually do that in 2 ways. I prefer this first way because I grew up doing arithmetic by hand. Back when I was in school, the calculator that I used ran on a 9-volt battery. I don't know if you guys even know what a 9-volt battery is. Maybe you've never had to use one, but they have these 2 prongs on the end, and you could actually lick the battery and feel it. It would send a sensation through your tongue. Like, it was weird. We didn't have cell phones when I was a kid. We just sat around licking batteries. Anyway, those calculators were super slow. So I needed to do things as efficiently as possible. And when you're doing things by hand, this first version is the more useful one. It's usually more concise. I'll show you in a second. However, there is another way to interpret this, and that's to put the exponent directly on the number under the radical. When you're doing the arithmetic by hand, this usually makes things harder. So this isn't my preferred method, but it is correct. Either one will work. Let me show you some examples. This first one says 16 to the 1/2 power. Well, according to our first rule, a 1/2 power is equivalent to a principal square root. So I can think of this as the principal square root of 16. I don't need to actually write this step in because that's what the first part means, but some people aren't comfortable with rational exponents and they're put at ease by seeing it as a radical. This is now the principal square root of 16. 16 actually has 2 square roots, 4 and -4, but the principal square root is 4 because that's the positive choice. The second example says 27 to the 2/3, and here's where my rambling about the 2 different ways to write this will come into play. I could rewrite this either as the cube root of 27 squared, like this, or I could square the 27 directly. If you're using a calculator, it doesn't really matter, of course. So the principal cube root of 27 is 3, and then we square that result. 3 squared is 9. If you do it the other way, then you're doing the cube root of 27 squared. That is, you're squaring the 27 first and then finding the cube root of that. That's much harder for most people. Like, I didn't have friends in junior high, so I've memorized a lot of these squares, and the principal cube root of 729 is 9, and I get the same result, but you can see how much harder that is. Again, if you're using a calculator, it doesn't matter which way you do it. In fact, you can just tell your calculator to do 27 to the 2/3 power. Your calculator can handle fractional exponents. The last one says 4 to the negative 5/2 power. Well, remember, a negative exponent is a reciprocal. I can rewrite this as 1 over 4 to the 5/2 power. And now we apply our new rule. I'm going to take the principal square root of 4 and raise that result to the 5th power. Alternatively, I could put that 5 directly on the 4, but 4 to the 5th is like 1024. I don't want to mess with that. It seems like it would be easier to take the square root of 4 first, then raise that result to the 5th power. The principal square root of 4 is 2. We raise that 2 to the 5th power, and that's 32, and we get 1 over 32. It's common to review the rules for radicals, and these are the two common rules for radicals, but I want you to recognize that these are just rules of exponents in disguise. Like the first one says, the principal nth root of xy is the principal nth root of x times the principal nth root of y. If I rewrite this in exponential form, it says xy to the 1 over n is equal to x to the 1 over n times y to the 1 over n. That's a rule we already know. So we don't need to look at special examples of this. This is a rule we already have. And it's the same with this. This is just x over y to the 1 over n power. And so that's x to the 1 over n times y to the 1 over n, which would be the nth root of x divided by the nth root of y. There's the rule right there. Because these are just exponent rules in disguise, we're not going to do any examples specific to those. I'm going to focus on the exponent representations. So here's an example. This looks a lot like the first example of exponents that we did before, where we're taking the product of two factors, each of which consists of a coefficient and then a variable raised to a power. Therefore, we're going to do this problem the same way. What did we do before? Well, we used the commutativity and associativity of multiplication to multiply the coefficients together. Negative 6 times 2 is negative 12. And then when we multiply the like bases together, we add the exponents. When you add fractions with a common denominator, you just add the numerators. This is 15 over 5. And 15 over 5 means 15 divided by 5, which is 3. As exponents add to 3, and so this is negative 12x cubed. One more simplification example. This says x to the 6th divided by 16y to the negative 4, all raised to the negative 1/2. There are multiple ways that you could approach it. So what I would do is my first step, and what you would do as your first step might be different things. My first inclination is to take care of the negative exponent inside of the parentheses. You might have another idea in mind, but I want to work inside the parentheses first. That's what the order of operations would tell you to do. You don't have to start that way. If you see that we have parentheses to a power and you want to start putting that power in everything, that's correct. But the first thing I would do is take care of this negative exponent. Now we said that that negative exponent leads to a reciprocal. This thing is already in the denominator, and so that's going to drag that up to the numerator. That's kind of a shortcut of what the rule actually says, right? I don't ever want to see you write this, but what that rule would actually tell us to do is write this as 1 over y to the 4th, right? And this would all be to the negative 1/2. But we call this a complex fraction for a reason, and we can simplify it. And the way we would simplify it is to multiply the top and bottom by y to the 4th. Then these would cancel, and the y to the 4th winds up on top, just like we have up there. But that seems like a lot of work just to get to something that's easier to describe by saying just drag this up to the numerator, find its reciprocal, and bring it up to the top. Again, we have multiple ways we could approach this. We can put this negative 1/2 on each of the expressions. We cannot add these exponents together because the bases are different, right? That rule only applies to common bases. So don't try to simplify that expression because you can't do that. But what I'm focused on is this negative exponent. This says take the reciprocal of the base. And so just like in the fraction example we did before, I'm going to flip the whole thing. When I do that, that makes the exponent positive. Now we have that quotient rule that we didn't use before. And that rule says that when you raise a fraction to a power, you raise the numerator to that power and the denominator to that power. And our numerator is a product, so we're going to raise each of those factors to a power. In other words, we're going to consolidate these into a single rule and just raise each and every factor to the 1/2 power. In the denominator, we're raising a power to a power, and so you multiply the exponents. 6 times 1/2 is 3. 4 times 1/2 is 2. In the numerator, this is the principal square root of 16, and the principal square root of 16 is 4. That does not mean 16 times 1/2. That's 16 to the 1/2 power, which is the principal square root of 16 which is 4. We can't simplify this any further, so that's our final answer. One more type of example, and I want to bring this up because I know a lot of you are calculus bound, and this is a skill that you're going to need in calculus. We're going to rewrite some expressions using rational exponents. The first one is a standard example in calculus. We're not going to do the calculus part, of course, but I want to do the rewrite part, which is something that most people would need to do in calculus. We're going to rewrite the principal square root of x squared plus 4 using a rational exponent. What does that mean? Well, I want to rewrite this as an expression that uses an exponent instead of a radical. We've just done an example where we used a 1/2 power as a principal square root. So I know I'm going to raise something to the 1/2 power. And what do I raise to the 1/2 power? Well, whatever's under the radical. So this is x squared plus 4. And that's our rewrite. You don't go any further. You certainly cannot distribute this exponent to those two terms because they're separated by a plus sign, not multiplication or division. Pause the video and see if you can rewrite the second one. Here we would do something similar, but we want to use a 1/3 power instead of a 1/2 power because this is a principal cube root instead of a principal square root. Then we just write in the expression that's underneath the radical, showing that that entire thing is under the cube root. And again, we're done. We cannot simplify. I know it's tempting to take 1/3 of 3, but we're not allowed to do that because of the plus sign. This seems like a meaningless exercise because we did nothing else with it. But I wanted to demonstrate it for two reasons. One, this is a skill that you're going to need in calculus. For those of you that are calculus bound, you'll all have to be able to do something like this. And secondly, it gives me a chance to remind you that you cannot distribute that exponent for the same reason that you cannot take the cube root of each of the two terms. That's not one of the allowable rules of algebra. It just doesn't work that way. It would be nice, but you don't get an equivalent expression when you do that. That ends our review of exponents and radicals. Make sure you take another peek at all of the rules. Make sure you get them down, especially the exponent rules. If you have any questions, shoot me an email or find me in an office hour.